Hi, this is Professor Fernandez, and in this video we are talking about Module 3 in Lesson 14. We're still talking about parametric surfaces as the broader topic. In this module, we're talking about surface area specifically. So I've drawn a few diagrams here to get us started, and the idea is to motivate and heuristically derive the equation for the surface area of a surface that we are defining parametrically. So the first thing I've done over here on the left-hand side is I've drawn the region UV in the UV plane. The domain that we are going to pick out are UV values to then map via the parametrization onto the surface to generate the parametrized surface. The next thing I've drawn is I've drawn a few grid curves here. So you'll notice on the left here, I drew this line, this one, and this one, and then I drew on the function on the right-hand side over here where those grid curves end up on the surface, I should say. And what I've anchored over here on the left-hand side with this blue dot here is a point that then gets mapped onto the surface over here. So then what I'm trying to do is I'm trying to illustrate how you could, for example, think of this square, this red square on the left-hand side, that is being taken as a rectangle or square, in this case in 2 dimensions, and being mapped by the parameterization onto the surface S. In general, when we do that mapping, we don't expect to get another flat surface on S. S is in general very curved. So we get this green curvy patch, if you will, on the surface S. And then the notion is that if we're talking about surface area, the surface area of S, the area of this blue surface, how can we represent that as the sum of surface areas of all these little patches? Well, so if we go back to our rectangle here in the UV plane, then notice that when it gets mapped to the surface, this little green patch, like I said, don't generally get another flat surface. I get something that's a little curvy, like down here. And because I had drawn these 2 grid curves, this one up here and this one up here, and then this one and this one, then I can start thinking about how, if I start at my blue point over here and traverse this red rectangle, how I might relate what happens on the surface to the derivatives of the parametrization R. How would that make sense? Well, if I start at my blue point here and I move along this grid curve over here, I am keeping the V value constant, and I'm only moving along U. So if I think instantaneously, what happens at this point then is that along this grid curve, I'm looking at R, or at this blue point, I'm looking at R sub U at this blue point. Right? And that's going to give me information about how I'm going, how the surface is changing in that direction over here on the surface along this grid curve at the point, the blue point. Great, so I'm like down here now, and I have information about that change. Suppose I then multiply this RU, partial derivative, times a small delta U. Right? So I'm trying now to sweep out this red rectangle on the surface S. Well, so then I'm over here. So I've gone this far. Now, suppose I go back and I do it all over again. I start again at my blue point, but instead of looking at a constant V grid line, I look at a constant U grid line. So here is my constant U, and then the vector that points in that direction instantaneously at the blue point is R sub V, because I am holding U constant. If I take that vector and I multiply it, that vector evaluated at the blue point, and I multiply it by delta V, right, then I am getting some approximation of this length of what happens on the surface S. So I am down here in this diagram generating this approximate distance, change in distance. What can I do now? I can now form the parallelogram from these 2 vectors, RU times delta U and RV times delta V. And back from lesson 3, one of the practice problems, we had talked about areas of triangles as the norms of cross products of vectors. We can double that, if you will, and get the area of a parallelogram as the norm of a cross product of two vectors. So we can see from everything I've tried hard to set up here that the area of the green patch, this little patch on the surface S, is approximately the area of this parallelogram, right? Approximately. And the area of that parallelogram is the cross product of these two vector lengths. So cross product of RU times delta U and RV times delta V. And if we use some properties of cross products, namely that if we have numbers multiplying the vectors that we're taking cross products of, we can pull those numbers out as multiplicative constants, assuming that they are, we take the absolute values of them. Here we're thinking about delta U and delta V as positive changes, so they come straight out, so we don't have to worry about absolute values. Okay, so this is enough to motivate the conclusion, which is that the area, the small patch of area, this green patch here on the surface, is approximately the norm of RU times RV at that blue point that I keep referring to in all of these diagrams, at that point, times a small change delta U delta V that is connected to mapping this UV rectangle to generate that green patch on the surface. And, I've done things this way to subvert and avoid the usual, X star, Y star, Riemann sum approach, just to get you moving a little bit away from that to a little bit more of an intuitive understanding of how all of these formulas for surface area, for surface integrals, line integrals, all these integrals are derived, moving a little bit away from the formalism of Riemann sums, but still retaining some of it and using more intuition to guide us. So you can see that if this little patch of the surface has area approximately equal to this, then to get the surface area, I would just do the same thing in all these other patches, right? So there's going to be some double Riemann sum here, where I'm adding this quantity as U and V change throughout, in this case, the UV domain that generates then the surface via the parametrization. And then, of course, the usual argument, as the change in U and the change in V get smaller and smaller and smaller, these double sums become double integral. And that then gets us to this definition. So what does the definition say? It says, suppose I have a smooth parametrization of a surface S defined over closed and bounded domain D. Excuse me. The closed and boundedness of the domain D, again, is for simplicity and ease of use. Many of these definitions can be generalized in many different ways. We won't go there. We will just be content with considering these nice cases, for example, smooth parameterizations on closed and bounded domains. The surface area of S, then we define to be exactly how we just derived this. So this is the double integral over the region D, where S is defined over, of the norm of RU cross RV, dA. So this is, on the left-hand side, another notation for this. Notice the subtle differences. On the left-hand side, where we have a ds. This is literally to be thought of as the actual area of the curvy element, or the curvy patch on the surface. So in other words, the actual area here we would call ds. And then this portion, norm of this times du, or times dA, we would call the area stemming from what we had done here, starting in the UV plane, multiplying that du dv by the norm, and then generating the patch on the surface. So as before with line integrals, where we saw that d little s was the norm of r prime of t times dt, here we are saying that, and this was a small change in arc length, infinitesimal change, was related to effectively the speed times the distance times the time elapsed. Here we are saying that this small patch of surface area is some factor RU cross RV times the rectangular area, if you will. So I'd like you to think about these two as expressing the same concept. If I take a linear or rectangular quantity, this is a difference of 2 times, this is an area, and I multiply them by some norm of a derivative of a parameterization, I get some insight into a curve, something, a curve, an arc length, or a patch on a curved surface, the area of that patch. So in that sense, this is effectively can be viewed as a generalization of what we were doing with line integrals to the surface, parametric surfaces setting. Last thing I'll mention here is I also want you to understand this left-hand side as noticing that the integrand here is 1. So remember again, we had in the double integral context discussed about the fact that if you take a double integral over R of a region dA, then that gives you the area of R. And if you take a triple integral over some, solid bounded by B of dV, that gives you the volume of B. It's in this sense that I also want you to understand this. If you take the double integral over a surface S of the surface element ds, you are going to get the surface area of that surface. Great. So with all of those different ways to understand what we've done and this definition out of the way, let's go ahead and work through an example so we can see some of these concepts in practice. So here's the example. It says calculate the surface area of the portion of S of the cone x squared plus y squared plus equals z squared lying above the disk, this. Okay, great. So the first thing I'm going to do is try to sketch out this cone. All right. So how would I do that? Well, we haven't sketched out a lot of cones, so I'm going to talk, in the course, so I'm going to talk a little bit through that. But basically, we can look at level curves. So if z equals some number, then the level curves I'm looking at are x squared plus y squared equals k squared. These are circles of radius k, and they're all centered at the origin. So I would start at x equals 0, y equals 0, z equals 0, and then as I move up in k, my circles get larger in radius. So I generate my cone that way. Great. Next thing I'm going to do is, I've visualized the cone now. How about the actual portion of the cone lying above the disk, x squared plus y squared is less than or equal to 4. So I'm going to draw a new diagram here because I want to draw the circle in the plane. This is the boundary of this set is a circle of radius 2. There we go. And the actual set itself, because of the less than or equal to, is everything included inside that. So let me just unclutter here. And then if I go back and I draw my cone, then my cone at some points, and we can calculate this, at z equals, let's see, 2 up here, z equals 2, I am going to be at x squared plus y squared equals 4. So at z equals 2, my cone has enlarged to cover exactly the same projected region as this disk given in the plane. So that makes it a little bit easier to draw my cone. There we go. And then, so what do I want to calculate here? The surface area. So if I go back to my definition, I'm going to want to parametrize the surface. And then just like what we've been doing in this lesson and with previous lessons with line integrals, once I parameterize the surface, I will then calculate some derivatives and calculate the norm of this cross product. Great, so I want to parametrize the surface. I'm dealing with a cone. So I'm back to figuring out how to parameterize surfaces. And anytime you see any x squared plus y squareds, sums of squares, you should probably think polar coordinates, right? That was the takeaway from doing double integrals in polar coordinates. So this is one thing that I can go back to. And in polar coordinates, x was r cosine of theta, and y was r sine of theta. I could stick with that same r, but just because we are dealing with u's and v's, I'm going to say that x is u cosine of v and y is u sine of v. Again, to stick to our parameterization standard notations of u and v. Great. If I do that, then x squared plus y squared used to be r squared. R is like rv, so that's u squared. And this cone is defined by x squared plus y squared equals z squared. So over here, x squared plus y squared equals z squared tells us that z equals u. You might wonder, why isn't z equal to negative u? That would yield negative z values. And in our cone, right, we are not considering negative z values. We're told that we're lying above the disk, x squared plus y squared less than or equal to 4. So we're looking only at positive z values. So we have now arrived at our parameterization, r of u, v. The x component is u cosine of v. The y component is u sine of v. And then z is just u. So now we have to figure out how these parameters range. So let's think about what everything is here. U, again, was like r. And r was like our polar distance from the origin. So we are now looking somewhere in the UV plane, which has become the r theta plane, r theta axis. And we're trying to calculate the surface area lying above this disk. So we're going back here now. And from this is where we extract r and theta. So from here we see that we're looking at a circle of radius 2. So u, which again is like our r, ranges from 0 to 2. We get at most 2 units away from the origin in this disk. And then we're looking at the entire disk. So we're not, for example, looking at this disk, where we exclude some of it, or we're not looking at a half disk. We're looking at the whole disk. So that tells us that v, which is like theta, goes from 0 to 2 pi. So that is our range for v. So this now completely specifies the parameterization. I have the actual parameterization, and I have the bounds for the parameters involved. So now the rest of it is just effectively going back to this definition and trying to calculate this right-hand side, and then certainly this double integral. Great. So I'm going to do that in a variety of steps. The first thing I need is I need RU and then RV, and then I need to calculate their cross products and then the norm of that. So it's kind of a few steps to do. So RU is the derivative, partial derivative with respect to u. So I'm looking here, that just gives cosine v. Looking here, that gives sine v. And the partial derivative with respect to u over here gives me 1. Great, so that was fairly straightforward. And then with respect to v, I'm looking here, I differentiate cosine v. I get minus u sine v. Looking over here with respect to v, I get u times cosine of v. And then over here, there is no v, so I just get 0. Okay, at this point, we're now going to calculate the cross products of these two. So let's give ourselves a bit more space for that. So this is I hat, j hat, k hat. And we have cosine v, sine v, and 1. Minus u sine v, u cosine v, and 0. So then we write this out. We have cosine v, u cosine v, and then sine v minus u sine v. That's I hat. And then alternates. So we have cosine v1 minus u sine v0. That is j hat. And then our last term, which is, oh, and I noticed, let's see, in the I hat term, I put, actually this is the j hat, this is the k hat term, so I'll put this over here. The I hat term is obtained by deleting this column and this row. So that gives us sine of v and 1, and then u cosine v and 0. Great. And then this is the actual term that you obtain by deleting first row, last column, which is the k hat term. Okay, great. So we've written everything out, and now we just have to calculate away. I'm going to put the k hat here. Okay, so this first one just gives me sine of v times I hat. Okay, great. And let's see, what else do we have going on? So for this j hat, I get minus, this product is 0, and then minus this, which gives us u sine v, and that's j hat. And then this one over here is going to look complicated, but it'll simplify because I have cosine v times u cosine v. That's u cosine squared v. Then I have minus u sine v times negative u sine v times sine v. So I get plus u sine squared v. Okay, hats. So my cross product here is sine v minus u sine v, and then this just collapses to u. So that is pretty nice. And let me just double check that everything looks good here. There might be one thing that I might have missed. So let's go back and check the x component again. So we had this, and this looks good. Yes, there is one thing I missed. So this product here is 0, and then minus this is minus u cos v. So that explains it. So this over here should be minus u cosine of v, and that trickles down to down here, minus u cosine of v. Great. Okay, so this is our cross product, and then we take the norm of this. So we're running out of space a little bit, so I'm going to remove some of this earlier content. So we take the cross product of this, and then we set up the double integral. So you might be thinking, this is a lot of work. And I would say generally, yes. And this is going to be somewhat characteristic of this portion of the course. As you near the end of almost any math course, you start using more and more of the concepts in integrative ways that you've learned throughout the first portion of the course. So then those concepts kind of stack on top of each other. You can see that here. We are calculating derivatives of vectors, vector valued functions. Then we're taking cross products. We're using determinants. Now we're about to calculate a norm, and then we'll do a double integral. So that explains the length and complexity of these things. Anyway, back to here. So if I calculate the norm of this, so norm of RU, norm of RU cross RV, that is the square root of the sum of squares here. So I will just talk this through. This would give me u squared cosine squared v plus u squared sine squared v. So that just factors out the u squared to give me u squared. And then plus this other u squared, so I get 2u squared. So at least we are rewarded with a nice simplification of this. Okay, so this is technically 2 times the absolute value of u. However, if we look back to our bounds for u is positive. So this is actually 2u. We don't have to worry about the absolute value. So then if I go back finally and I calculate or set up my double integral for the area, this is what I'm putting in, 2u, and then my dA here is du dv. Great. And yes, so far so good. And then I have to figure out my region of integration. Well, this is the region that I now go to the UV plane to look at. Okay, and the UV portion of things, here we go. X equals u and y equals, x equals u cosine v and y equals u sine v. This was the parametrization which I erased of, you can see it here, the portion, the disk in the plane of radius 4, of radius 2, because we have x squared plus y squared less than or equal to 4. So again, going back to what we had already said about the bounds for u and v, right? U goes from 0 to 2, and v goes from 0 to 2 pi. 0 to 2 pi. Great, so thankfully we are now down to an integral that is fairly straightforward to evaluate. So when I integrate with respect to u, I just get u squared evaluated from 0 to 2. And that gives me 2 squared is 4. Great. And one thing that I did notice, so this square root should be there, should be there, should be there. So that changes things a little bit. My integral would be u squared over 2 times that square root of 2 left over. So good thing we caught that. So I have square root of 2 over 2 times u squared evaluated from 0 to 2. That just gives me 2 squared, which is 4. Great. So then I'm just going to pull all these numbers out. I have 2 square root of 2 integral from 0 to 2 pi dv, and then that just gives me a 2 pi out of there. So my final answer is 4 pi square root of 2. And this is a legitimate surface area of this portion of the cone that we've left here, which lies above x squared plus y squared less than or equal to 4. So if you were to actually measure, if you could do this in some way, maybe you use some paper and cut this out, you could measure this surface area. It would be 4 pi square root of 2. The last thing I'll mention here is that if we go back to our definition here, sometimes, like with line integrals, where we saw it may be possible to interpret the line integral as the area of a curtain, sometimes the integrand would be negative, and we would have to interpret this as the net signed area of that curtain. This is never going to happen, at least in this particular context, because the norm that we're integrating over here is always positive. So you're integrating a positive function over a domain, right? So you can see also that from here and just from the notion of surface area. So all the numbers that you get from evaluating such integrals are really honest-to-goodness areas. You don't have to think of them in the net or the signed version, as we did potentially with some line integrals. Okay, so that's it for this lesson, this module, and I'll see you in the next one.